Thank you all for giving up your lunch hour to come listen to me. Hopefully there will be something interesting. Excited to be here at this Energy and Efficiency Institute. So as Ben was saying, I work on multiple things, but my background is in control systems. So I'm a hardcore control theory kind of guy. My application is, but all of my work is applied, and I apply control systems techniques to two main areas within the field of energy and sustainability. One is on efficiency of air conditioning systems. How do you make air conditioning for large buildings more efficient through the use of advanced control techniques? The other side is kind of slightly away from that, but still connected to air conditioning systems, is how do you use the flexibility inherent in many of these loads to help the power grid deal with the volatility of renewables, right? So it's kind of like, I call it virtual batteries. So you can use buildings to kind of vary their power consumption up and down a little bit to make them behave more or less like batteries from the point of view of power grid. So the previous two talks in Santa Barbara and LBNL were on different aspects of that. But since I'm in the Energy and the Efficiency Institute, I thought it was apt for me to talk about efficiency properly instead of mixing it all up with power grids and all of that. So today I'll be talking about efficiency. Okay, so that's the title. Anyways, so this work that I'm going to present today was done by two of my graduate students, Ting Ting and Naren. And of course, would not have been possible without financial support from NSF, DOE, and an ongoing grant from Florida Department of Agriculture and Consumer Services. So list of parts, that's not really important. Motivation, I guess, for this audience, I don't really need to motivate why energy consumption in air conditioning systems is important. We know they consume a lot of energy. Important thing is that, of course, there are two ways of fixing that problem. One is to build more efficient equipment, and that's something that I cannot contribute to, that people in this room can contribute to. But there is also another aspect to that potential, which is to improve the control system. And there is, in fact, a lot of potential in reducing energy use of air conditioning systems by improving the control system. And that comes from the way the control systems are designed and operated, because mostly right now, they're controlled based on set points that are designed. The set points themselves are designed based on decades of engineering experience and quite a bit of research work, but still they're kind of static because these are complicated systems. So this is a kind of a air conditioning system you would see in many modern buildings, definitely in hot, humid climates. So there's a cooling and dehumidification coil. So if you're in Florida, the dehumidification part is not important. Actually, it's sometimes the opposite. You need to humidify by the air. But in Florida, you need to cool and dehumidify the air, then supply to the rooms. Then you have to make sure there's enough air going into every zone. But then this air, because it's dehumidified by cooling it quite low, so it's dry and cold. So if you supply too much, then the zone becomes cold. Then you might have to reheat it. That's part of the reason why it is inefficient. But of course, it's not very easy to say, well, why don't you then just stop reheating, because then it will become too cold. And if you reduce the amount of airflow, then you don't have enough ventilation. So there are all these constraints. And the HVAC engineers over the years have come up with a set of really good rules to help kind of make sure that the buildings are maintained to our preference to the extent possible. But they're not, the control systems are not super intelligent. So for example, the set point for this air coming out of the cooling coil typically is kept at 55 degrees Fahrenheit. That is to make sure it's dry enough, right? And there are some setbacks, but then there are PI loops maintaining that 55 degrees Fahrenheit. Whereas the buildings are never in steady state, outside temperature is changing, the load inside the building is changing because people are moving in and out. Because of that, you actually want to, this is not the best decision at all times. This is the best decision at certain times, but not at all times. So what you really want to do is do online optimization based on the current situation. And the role for optimization comes from the fact that you can have many possible decisions that will lead to the same indoor climate, but will have very different impact on the energy consumption. So for example, if you want to provide a certain amount of cooling to a building, you can reduce the airflow, but cool the air a lot. So there are two things, the airflow rate, and the other is the temperature of the air going into the building. So you can cool the air a lot, but supply a smaller amount of air. That'll provide some cooling. But you can also do the opposite, supply a lot of air, but not cool the air so much. So because of, and both of them will have the same amount of cooling delivered to the room, but as you can imagine, these will have two different impacts on energy consumption. So that's where now, because you have multiple choices that will lead to the same output, but has different impacts on energy consumption, that's where optimization comes into play, right? So this is actually a prime example where you can use optimization to do something, something better than what's being done now. So that's kind of what this part of my research is about. And in fact, there's quite a bit of work that's been going on in the building sector, trying to use this advanced optimization-based algorithms to make buildings more efficient. So one of these optimization-based techniques, you might have heard this name. This has become a really powerful technique. It's used in everywhere from aerospace to automotive, and now people are trying to do this in buildings, is something called model predictive control. So what it does is that there's an optimizer, and you pose an optimization problem for some finite horizon. So right now it's at 12 p.m. And you plan for, let's say, next 24 hours or next 12 hours based on your best idea about the next 12 hours. So you know that the weather, you have a weather forecast for next 12 or 24 hours, and you have some idea about the kind of number of people that might come in the building. And then you have some ideas about if you make different decisions. So U is the control decision. So that may involve airflow rates, fan speeds, chiller set points, etc. And the W is the disturbance, that's like outside air, outside ambient conditions, weather. So that will lead to some temperature and humidity in the building. And there is a relation between the two, which is this equation. So from current time to some time in the future, you plan for it and solve this optimization problem. And whatever comes out of it, you get a plan that this tells you the optimum thing to do from now till next 24 hours is this. So you might have some time varying control trajectory. So what you do is that you implement the first bit, which might be the first 5 minutes or 10 minutes or even an hour. And then at the next time instant, you resolve the whole thing again, because by that time, things have changed. Maybe you have better forecast, or maybe the initial conditions have changed. The state estimator might give you something different. Because things have changed, you resolve the whole thing for the next 24 hours. And then you can just go on and on. It's called a receding horizon optimal control or model predictive control. So it's a very powerful technique. And so people are trying to do this for buildings, at least in academia. And even industry is kind of getting interested in this too. So there's a recent project in the Stanford campus by Johnson Controls that they are using MPC. So if it is so great, why is not everybody using it? Well, you need these models. You need to know for every possible decision I might make, what is the effect on climate and energy use? And these models are not easy. So those of you who work on HVAC, you know that these are complicated systems. The other thing that is important to solve it, because I'm planning for the future, and the building in the future is going to be affected by future disturbances. So how many people are going to come in, or the heat load that's going to come into the building at 5 p.m. today. I need to know things like that. So I have to have this prediction. All of that has to go into this optimizer. And how do you get these predictions? It's not that easy. So I'm going to specialize to just a simple building for this talk, although we can apply these techniques to more complicated things. So there's a single zone, and there's a cooling and dehumidification coil. So there are 4 things that you have to choose. These are the control commands. These are things that we implement through software. So one is the return air ratio and the supply air flow rate. So total air that goes into the building, and also the fraction of that comes from the outside. The outside air fraction is important for ventilation. And then these 2 temperatures also can be controlled. So the conditioned air temperature is controlled through a chilled water flow rate and chilled water temperature, but let's say all of those things are fixed. You can only control this valve to control this temperature. Once you control that temperature, that changes the humidity, because both of those are important. And then once you change the conditioned air temperature, the other thing you want to do is sometimes you may have to reheat, because otherwise the building will become too cold. So what I call the supply air temperature, you can change that also by using a reheating coil. So these are 4 variables that you have to choose. Humidity is something that you really like to control, especially if you're in Florida, but we cannot control humidity directly. The only direct control we have is the temperature of the conditioned air that indirectly changes the humidity. So these 4 variables are what I need to control, what I can control. Of course, actually the problem is not just 4 variables, it's 4 variables if I update my control every 5 minutes, so it's 4 times however many samples, right? So these are the variables I have to optimize over. So this is kind of how the whole software is going to look like. This is your controller block. It is going to take disturbance predictions, and then it's going to compute these 4 variables for the next 24 hours. And that has going to go into the plant, which is the real system. And it is going to be affected by the disturbance, which are solar radiation, outside temperature, outside humidity, and the heat produced by the occupants, and etc. And of course, the actual disturbance is going to be different from the true disturbance. So there's a feedback loop, because these measurements come back to the controller, and that's why the MPC controller kind of keeps repeating the same thing over and over again. That's how we get feedback, which gives us robustness to these uncertainties. All right. So you need 2 things. The model, you need 2 things. One is the equipment model, so cooling coil, chiller, etc. And the other thing you need is also the thermal dynamics. So you need to know, if I change any one of those 4 things, how does it change the temperature and humidity inside the building? Ultimately, that's what you need to control to keep people happy, right? And disturbance also has 2 main components, categories. One is weather related, which are easy to predict because you can just go to Weather Underground and get a forecast. But then there are all these other things that are also important, which are heat gain due to occupants and our behavior. If you're using a coffee maker, if you're using a computer terminal, those things produce heat, and that has an impact, non-negligible impact, and you need predictions for that as well to actually make this thing work. So although there's a lot of interest in applying MPC for buildings, this is kind of a Google Scholar meta-analysis, number of papers on MPC for buildings that was published in the last few years. So you can see 2014, there are 42, 2015, there are 47 papers that are published according to this particular study. Although there's a huge interest in the academic community, there has not been a whole lot of translation to practice. We don't see a lot of industry kind of picking this up quickly, except for Johnson Controls, who is actually trying to do this. Not trying, they have actually done this in a Stanford campus. And the academics who have studied these things, they have also pushed it to the extent possible. I mean, they have actually done experiments on real buildings. So why is it not getting adopted by the industry? Well, I mean, the vision is great, but to translate this vision to reality, there are some gaps, there are some challenges. It's not so easy. One is, of course, because it optimizes using this model. You need this model relating the disturbance and the control commands to the state variables, the temperatures, the humidities of all of this other stuff. And these models can be quite complicated and uncertain. So how do you get these models? That's one problem. The other problem is disturbance prediction. Weather prediction is okay. We can get it from somebody else. But all the other stuff, we need to predict that. And that's not easy. And humidity is almost always ignored, especially in the MPC literature, not in general the air conditioning literature. Air conditioning literature does a pretty good job in worrying about humidity, but the MPC literature has completely ignored it. Now in California, you might say, I don't really care, right? It doesn't really matter so much. In Florida, Southeast Asia, and many other places, actually you cannot ignore that. So I would say combination of all of these things have been at least one of the reasons why we have not seen a whole lot of transition to practice. So we have to kind of address at least these 2 first challenges, and also the third one, if you want to apply this in Florida. We have to have these models that are reliable, and we have to be able to figure out how to predict disturbances that will go into the optimizer. So the approach that I'm trying to push in my group is, so this is the word autonomy appears in the title. So I call it autonomous building, like autonomous vehicles, is that everything has to kind of happen by themselves 24/7, 365 days a year. So one of the problems with this modeling is that because HVAC models are so complicated, there's so much human expertise that is needed to fit these models, is that, you can fit a model to your building, and then you can probably do a demonstration, but then 6 months later, the model is no longer accurate. So you have to kind of go in and then muck with the model again. The other problem is that it takes a lot of effort to fit a model to one building, but then you want to apply it to another building. Every building, especially large commercial buildings, are all distinct. Now I have to repeat the whole modeling process again, and so the cost increases quite a bit. So that's so one of the things that I want to do is, how do I make it automated? Well, one thing I have to do is I'm going to use all linear models, which many air conditioning engineers, when they see this, like, oh, wait, that's not going to work, because we know these equipment are really complicated, dynamics are really complicated, we need non-linearities in the model. How are we going to use linear models? Well, I don't know how, I mean, I'll give you some ideas how to do this, but the reason the linear models are so important is that you absolutely have to have the models linear for your optimization problem to be convex, right? So what does that mean? If you already know this stuff, then this is kind of boring to you. If you have not, then it's a pretty simple picture. So when you say convex optimization, optimization problems can be convex or non-convex. Convex optimization problems are easy. Why? Because the cost function will look like this. So there's a single minimum, right? And when you say convex optimization, you mean an objective function has to look like this, a convex objective, but also the set, the constraint, the set of variables over which you search to find a minimum, that set has to be convex, has to be a convex set as well. And for the sets to be convex, these dynamics that relate the control command, the disturbance to the state variables like temperature and humidity, these dynamics have to be linear. If they are non-linear, these appear as equality constraints in the optimization, and any optimization problem to be convex cannot have nonlinear equality constraint. Any nonlinear equality constraint will make the problem non-convex. Non-convex means that not only can it have more than one minimum, which is one problem, but more importantly, you might have some very strange geometry like saddle points. So the algorithms that are designed to solve this problem, they'll get stuck. They'll never go anywhere. And then now, if suppose you have 5 minutes to compute the decision for the next 24 hours, before you go to the next 5-minute interval, this 5 minutes, the computer is just running and running, and at the end, it says no solution. And you cannot have an autonomous system running 24/7, 365 days a year if you have situations like that. So you must guarantee that every time you'll find a solution, that has to do with feasibility of the problem, but also you need convexity. So for that, all your models that have this form must be linear. Now, of course, linear models are simple. So if you have a very complicated dynamics, then it might be difficult to do so. So one thing that you have to do is the models have to vary with time. So you construct one model maybe for one day, and maybe next day you have to come up with another model, because that'll next day things have changed. So you need to have this underlying model identification loop that will automatically learn these models as things change. So that way you can have linear but time varying model that will make your problem convex, which will make everything nicer and easier. But at the same time, you don't lose prediction ability. Otherwise, if you insist on one linear model for 1 year, that's just not going to work. As the buildings are, that's how buildings are. So, and disturbance prediction, that's actually simple. This is the kind of main important point. So modeling, there are two kind of sub models that you have to worry about. One is model for all this equipment, including chillers. So I'm not going to talk about chiller modeling. That's actually very complicated. We haven't done much work there. The building in which you're trying to do experiments, the chill water gets supplied from somewhere else. So it helps us not worry about chiller. I have to model the cooling coil, how these control commands affect the temperature and humidity of the air. And I also have to model this part. So if after I choose all these control commands, including flow rates and temperatures of the air, how does it change the temperature and humidity of the zone? So these two sub-models I have to do. So the first one is this model from what I call the zone thermal dynamics. So how does the temperature and humidity of the zone get determined based on all the control commands and based on the disturbances? So here, control command, I have combined all the control commands into the heat injected or extracted by the air conditioning system, that's HVAC. And then there are these outside ambient condition, temperature of the outside air and solar radiation. The W is the disturbance, that is the unknown part of the disturbance. I mean, our ambient conditions can also be thought of as disturbance because we can't control them. But the tricky part of the disturbance is the disturbance that comes due to people, right? The heat gain due to our presence. That's completely unknown. Whereas ambient conditions are more or less forecastable. So this problem of how do you construct this model, of course you can come up with like, first principles based model using partial differential equations. You cannot use them for real-time optimization. They are too complicated. So people have come up with like simple models relating this to that, input to output. And there's a huge literature on that going back at least to 1990s, actually much earlier, probably like 60s, based on if you look at the ASHRAE Fundamentals Handbook. But problem with this literature is that they all ignore the disturbance, which is kind of funny, but that's how it has been. So they ignore the fact that there's a large unknown disturbance, which is the heat gain due to occupants and other things that are affecting the output. So this is 0. And what's the relation between this and that? Well, that can be done, but then it'll be incorrect. And the people who have recently tried to address that problem, how do you handle disturbances? They have used specialized test buildings where the disturbance is measured. I mean, you cannot use that in an existing building 24/7. So the technique that we came up with recently, our goal is to come up with estimate the disturbance and the unknown plant model at the same time. So remember, when I said my goal is modeling, I want to identify the plant model based on input-output measurements, but there's an unknown input, unknown disturbance. I'm going to identify this signal as well together with the plant. And you might say, well, that's impossible. Yeah, of course, it is impossible, right? So why is it impossible? Imagine you have this equation, y equal to ax plus b, and a and b are unknown parameters. So if I have measurement of y and measurement of x, I have one equation, two variables, I cannot figure both of these things out. Similarly, you have disturbance affecting and the control inputs through the plant model affecting the output. There's no way that I can figure out the plant model and the disturbance if I only measure the inputs and the outputs. So we have to have extra assumptions. So this is what we do. We use extra assumptions to enforce some structure on the problem that helps me do that. So we use, again, linear model. So we use a simple linear structure. All gets converted into linear regression. If you have seen this before, it's pretty straightforward. If have not, it's not really that important. So you get this linear equation. The phi is a known matrix of known things. Theta is where all the unknowns appear, the parameters of your model, and also the disturbance signal. So if you have data from time 1 equal to n samples, the W bar is the unknown disturbance from 1 through n, or 3 to n, but that's not so important. So the theta is what I want to identify, from knowledge of y and phi. And you cannot really do that because of the problem that I mentioned, even underdetermined system, actually overdetermined. So what we do is we say, well, we know extra things about this disturbance. All right, so this is occupant induced disturbance. That's the part that is unknown. And since you're dealing with commercial buildings, occupants come in the morning, they kind of more or less stay there. Maybe there's a dip during lunchtime and then they leave at the end. So I can approximate this as a piecewise constant signal. So if you think of the derivative of that signal, that will be mostly 0, right? Because hardly change except for a few jumps. How does that help? Well, because its derivative is mostly 0, so that disturbance signal, once you do the trend, this W bar signal is almost like the derivative. You can say it's mostly 0 with a few non-zero elements. And that helps because of something that has happened in another field about 20 years ago. I'll get to that in a moment. So I try to identify the thetas by solving this problem. So this is y minus phi theta 2 norm square. This is your standard least squares. If you do that, it's not going to work because it's an impossible to solve problem. I mean, infinite number of solutions. But then I add this extra penalty, and S theta gives you the W bar, and this subscript 1 means 1 norm. So how does this help? Well, there's this something called compressed sensing or basis pursuit, and it goes by various names. This idea came up in the 2000s. It has completely revolutionized signal processing. Now people are using it from genomics to economics, right? So the idea is that if you add this 1 norm penalty, then you get solutions that are mostly 0. So it's like looking for a needle in a haystack. So if you're some phenomena trying to model, and you think, I don't really know what that phenomena depends on. It might depend on these 2 billion variables. You feed those 2 billion variables, and you know that maybe 3 of those 2 billion variables actually affect the phenomena. And if you solve a standard least squares problem, what will happen is that you will get these 2 billion variables. The solution you will get, everything will be really small, close to 0. It doesn't tell you anything. So with this 1 norm, if you add this 1 norm constraint because of the way that their level curves are, so if you solve a 2 norm problem, then the solution will be somewhere here. Let's say it's a 2-dimensional problem, beta 1, beta 2. Solution will be there. That's got both the components are non-zero. If you add this 1 norm penalty, and there are some pictures you can draw, you'll see that with high probability, you'll get a solution which lies either on this axis or that axis. So this solution, the first component is 0. It happens also for much larger dimension problems. So that what happens is that at the end, the thing that you're trying to find, this beta could be a large vector, could be a million. Only a few of them will be non-zero. Everything else will be 0. It's kind of funny. But there are people that have shown this to be true. And because of that, it has had huge impact in all sorts of areas. Not so much in control systems, definitely not in HVAC. So we're trying to use that idea by adding this penalty. And then you can add some extra constraints to make sure that we get stability of the system. I mean, you cannot make a building go unstable by heating and cooling. So of course, your model should show that it's stable, but most of the existing work does not do that. So it's a convex problem. It guarantees all these properties. And that's basically it. That's the algorithm, right? It looks like it's a problem, not a solution. But because it's a convex problem, and it's got all these nice properties, you can feed it into a nonlinear programming solver, and it'll give you a solution like that. So once you get into this form, you can say my problem is solved. That's the algorithm, right? So we have done this for, evaluated for all sorts of simulation results, and it does actually pretty well. I guess these are not that, in fact, recovers the disturbance, but these are not very interesting because they are simulation results. So let me show you some results that we obtained by applying this technique to data from buildings. So we have this building, Pew Hall, in the University of Florida campus, and we collected data from a large auditorium of that building. So this is how the air conditioning power and the temperature of the building looks like. So difficulty in applying this method to existing building data is, of course, you can apply any method to any data, and it'll spit out an answer. The problem is, how do you characterize how good this answer is? Because it's supposed to give you a model of the building, how air flow rates and temperature of the air affect the temperature of the building. So it'll give you the model, and it'll give you the unknown occupant induced heat gain. Now we don't know what the unknown occupant induced heat gain. There's no sensor you can use to measure that. So how do you verify the answer? I mean, it predicts the temperature very well, but the important problem is the disturbance estimation. How do I verify that the answer I'm getting has got anything to do with reality? So the best you can do is we look at the answer and you see what the values turn out to be during night times, because it's supposed to be the occupant induced heat gain, and this is an auditorium where there are classes during the day. At night, it's almost always completely empty. So if the algorithm is doing something right, it should produce a mostly 0 answer at night, and because nobody's there at night. And this is what you mostly see. I mean, there are some spikes, but mostly it's close to 0 during night times. It is, I don't know if you can see it from a distance, but these gray areas are night times. So this tells us that we're actually getting something close to reality to the extent that we can verify this, right? And if I can extend this to, I've shown for like a single zone, but you can extend it to multiple zones, especially in this cubicle type areas, because this is something I'm really interested in, shared spaces. So suppose you have multiple VAV boxes, multiple control commands coming in, and that'll have impact in different locations in terms of temperature. So what I want to figure out is how does these control actions affect the temperatures in every zone, because they are also affected by their own individual disturbance. So this same kind of idea, I don't want to go through details of that, can be applied to this, and it'll give you a model, and it'll tell you which actuators affect which stations. So if you don't know anything, it could be that every VAV box will affect temperature at every station, but you know that's not true. So, and if you just try to solve the problem in a standard manner, it will tell you that the airflow coming out of this vent will affect temperature here, 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 everywhere. But we know that that's not likely to happen. It will probably impact this area much more than impacts other areas. So you are trying to get an answer where the graph connecting inputs to outputs is sparse, meaning there are not a whole lot of links. And again, the sparsity kind of enters there. You can use that to put an L1 penalty, and you get an answer. So again, we're trying to apply it to real buildings. Same problem. There's no ground truth. How do I verify that I'm getting something useful? So what we did was we picked 4 zones from 2 different floors as widely apart as possible, so that we can reasonably guess that there is no thermal interaction among these 4 zones, which means that the airflow or the control inputs affecting these zones should not affect any of the other zones. So our belief for this network is that U1 only affects Y1. So these subscripts are flipped, sorry about that. and there should not be any crosstalk. And in fact, when you run the algorithm, this is what the answer it gives us. It tells us that there is no crosstalk. So again, this is kind of the best we can do in terms of verifying what the algorithm is doing, because there's no way to figure out what the true model of the real building is. Right? A simulation is a different issue. So there is some related work, but none of them actually have these properties, especially the convexity part, which is really important to be able to make all this modeling, model identification a part of an autonomous control system that will update these models or learn these models online. So then, of course, there is so model I talked about so far models this part, right? Once you decide these control inputs, how does that change the temperature and humidity? But also you have to model the equipment. As I said earlier, we don't really know yet how to model chillers. That's a problem that we have not addressed yet. I mean, people in this room can help us. But cooling and dehumidification coil, that's really important. We have to model that. And so we have come up with some simple model for the cooling coil based on basically simulation data. So we come up with a surrogate model. We have these complicated models that you can get from Energy Plus or other sources, run simulations, and then you can fit a simple model that does a pretty good job. Now, these are actually not convex. So this is a problem that we are still trying to figure out. You still have to use non-linearities to capture the behavior because you have these curved surfaces. Linear models, you'll get flat surfaces. So we are not there yet in terms of getting them to be getting them to be convex yet. So we got these equipment models, not to the extent we like them, but we have this completely learnable zone thermal dynamics model that also gives us the disturbance estimate from the past. But to run MPC, run this optimization-based control algorithms, we need future disturbance. We need to have a prediction of the disturbance that's going to hit us in the next 24 hours. So we do that by using the data that comes out of these estimation algorithm. So we have past data. Let's say right now I'm here. I look at the last 1 week's worth of data. I run my algorithm and I get the estimates of this disturbance, which I don't know, but I can get an estimate. So the hat represents the estimate. Once I have these estimates for the past, then I look at the time series and try to fit a simple model to that time series so that I can predict it for the future. Let me go to this slide first. So this is a hypothesis saying that the disturbance at next week's disturbance, let's say, at a particular time, let's say next Monday's disturbance, will depend on previous Monday's disturbance, and also will depend on the outside temperature and humidity and all of this stuff. But more importantly, the schedule. So you have to know the schedule information, because if the end of the summer or if the summer, the schedule will be 0, let's say, or 1. And that will produce one kind of occupancy pattern, which will produce one kind of disturbance. Whereas if it is, if the classes are ongoing, then you'll probably have more people, you'll have more disturbance. So you come up with a model like this and you fit these parameters by looking at all the existing disturbance estimate that you already have. And then in real time, now you can use this model to predict, because all of these things, because this is the past disturbance that you already have. The other things, the temperature and the solar radiation and the humidity of outside, these are forecastable from a weather forecast. And the schedule information, presumably you have that, right? If you, yes?
I'm still a little lost on practically how you measure last week's disturbance. Like, how do you know?
We don't. Okay. So this also has this hat. It is the last week's disturbance I estimated by using this algorithm. There's no way to know any disturbance at all, right? So I estimate last week's disturbance. So I'm right now, I guess this is a good time to go to this slide. Sure. So let's say midnight tonight, I have to come up with disturbance predictions for tomorrow so I can feed into the optimizer. I have previous disturbances that I'm continuously learning this algorithm to estimate previous disturbances. I don't know the previous disturbance. I'll never know that, but I'll estimate that. So once I have these estimates, I fit these models, and this model's already there with me. Then I just feed into, so by fitting this model, I mean I have estimated these parameters alpha 1, alpha 2, alpha 3, all of that. And then I use the weather forecast and a schedule forecast to predict what the disturbance is likely to come next week or next day. Okay. So this is a completely time series model because because this is supposed to tell us, what the occupants are going to do, which is, and there's no Newton's laws for occupant movement, right? So this is not physics-based model. This is a completely time series model. So only thing I'm doing is I'm using knowledge of these previous signals, right? So there is no heat balance equation or anything like that here. And just using previous samples to fit this model, and whatever I get, I get. So that's the problem with this, but that's what we've got. So sometimes it works really well. So this is one of those, if you ask your students for slides, they give you the best slide ever, but it's not does not quite get the full picture across. So this is what we did for, so W hat J is for the jth week, and W hat J plus 1 is for the next week. So these are disturbance estimated from 1 week and the other week just from data. And this double hat is the one that was predicted for the next week by using previous week's estimate. And all of these things line up perfectly well. Well, it's not surprising because it's very predictable. It's a nice pattern. It's not going to work out this nice every week. All right. So, but sometimes you are able to predict it pretty well. So with that, actually, we can run this MPC controller. Okay. So we have developed this control algorithm, and I call this the SLMPC. So S stands for sensible, L is for latent, because we want to include humidity in it, because a lot of the previous work has ignored humidity. Now, of course, when you include humidity, everything gets much more complicated because you have the cooling coil models, and you have to talk about the humidity dynamics, which I did not show. It's a simple, like a mass balance type equation. So then the question is, okay, is it worthwhile to go through the extra level of complexity? And there, to check that, we also implemented another algorithm, which is algorithm, again, an MPC algorithm taken from the literature that has ignored humidity in the whole problem formulation. And finally, a third one we compare against is so it's called single maximum. It's commonly used rule-based control algorithm that is used to control equipment and VAV boxes in buildings. So that I call baseline. And we fitted these models to data from this large zone in Pew Hall. It's a auditorium. It's got one large AHU, which average air flow rate of about 4,000 CFM. So we kind of do the simulation. We fitted the models to that particular building data, so we know that we are not completely cooking everything up. So this is how the MPC Optimizer looks like. It's a mess. So I'm trying to simplify it or represent it in a simple enough manner. So the planning horizon is 24 hours, and everything is updated every 5 minutes. So in 1 hour, there are 12 samples. So 24 times 12, that's like 288 samples. So your planning horizon, you're optimizing over 288 times 4 control commands, because at any given time, you have to choose these 4 variables: flow rate, temperature, 2 temperatures, and a return air ratio. And then there are 288 of them over the 24 hours. And then there are actually problem dimension is much bigger because of the dynamics that introduce all the extra state variables. So this is the first problem we solved. So the cost function you're trying to minimize is really simple. It's just the total energy use by the building. Of course, you can add demand charges and all sorts of other things, but we haven't done that yet. And subject to all these constraints, zone temperature dynamics, which I showed earlier, humidity dynamics, which I did not show. It's a first order differential equation. And cooling and dehumidification call dynamics, which I showed earlier with these complicated curves. Then there are, of course, constraints. You have to make sure the zone temperatures are within these bounds, humidity is in the bound. You cannot reduce the flow rate too much. You have to maintain a certain amount of outside air flow rate for ventilation. And of course, actuator constraints, your fans can only push this much air. And the building has to be always under positive pressurization. Because this was kind of interesting. We discovered it kind of funny. We should have known about this earlier. We know that buildings typically are positively pressurized, but if you're trying to just minimize energy use, your optimizer might say at some point, if nobody's there, building is completely empty, shut everything down. And that's not good, especially in a climate like Florida, because you don't want infiltration, and moisture might come in, stay in the cracks, cause trouble. So, I mean, that's as much as I'm going to describe the control algorithm, because the details are in the papers, but it's not really that exciting, right? So I'll jump to the results. So the results you obtain can be summarized by these two lines. Temperature is maintained within the bounds by all the three controllers, right? The baseline controller, which of course we know it will do because it is designed to do that. And also that MPC controller that we design, and also the one taken from literature. But humidity is maintained only by the baseline and the proposed MPC controllers. The MPC controller, the sensible heat only MPC that is taken from the literature, that does not maintain humidity. Not surprising, because humidity is not part of the problem formulation. Now, baseline of course maintains humidity and temperature, but the way it maintains humidity is by using these very aggressive conservative control commands, like keeping the supplier or conditioner temperature 55. And because of that, the baseline controller expends a lot of energy, and this MPC can actually save a lot of energy by optimizing, by recognizing that you don't always have to keep the condition air temperature at 55. So here are 3 bar charts for 3 different climate conditions. All the simulations are done for weather patterns for Gainesville. We are doing it for other locations, but these are the results that I have so far. So this is a hot day, mild day, and a cold day. So summer, winter, and the spring. And this is the energy totally used in a particular day for that one particular zone.
How is the humidity-based controller beating the sensible only if you're trying to take care of a whole other variable?
So as you can see, it's not always beating the other MPC controller. It seems like it should be losing in terms of energy use. It might actually lose in California, but in Florida, because humidity is such a big concern, right? So in cold day, they consume, both the MPC controllers consume the same amount of energy. And the other 2, hot and mild, they do kind of similar. It's doing slightly better, but not much. But compared to baseline, it's actually saving quite a bit, especially not so much in hot days, because hot and humid days, what happens is the heating load is so high that there's not a whole lot of room for optimization, right? Because baseline control is designed pretty well. Now this is our simulated baseline. In an actual building baseline, I don't know, it probably is doing not so well. So in a real building, you might be able to save more. But in a cold day, this conservativeness, you can really exploit that to save a lot of energy. So seems like, okay, any MPC controller is fine. It'll save you energy, but only the one that we proposed with humidity part of it, which makes it more complicated, is the one that will give you humidity control. So why does that happen? Well, it's more pronounced in the mild weather, not so much on the hot weather. So this is a simulation from in a March day. These are about 24-hour duration. So this is, I think it's 8 a.m. to 5 p.m. So this is the working hour, so occupied hours. So temperature bounds are tight. Humidity bounds are kind of the same throughout. And during the unoccupied hours, the temperature bounds are loosened. So this orange looking line is the MPC controller that does not care about humidity. The green line is that does care about humidity. And the blue line is the baseline controller that uses rule-based control. So all of them are maintaining temperature quite well, but the one that does not care about humidity, this is the one that screws up on the humidity, whereas the one with humidity just barely hugs the upper bound. So what's happening is that humidity constraints are active. It recognizes that if it takes control actions to reduce energy use, then you lose out on humidity. Whereas the one that does not recognize that, it says, well, there's not enough heating load, so I can use free cooling from outside air. That's basically what's happening. On a mild spring day, it says outside is cold enough, I can just bring in outside cold air and provide free cooling. But what happens is Florida, right? That's in California, the same thing will not happen. Florida, even on a mild spring day, there is a non-trivial amount of humidity. You cannot use that all the time. Maybe you can use it for some time. If you bring in, you get this humidity violation. Now, of course, you might say, well, who cares? It's at nighttime, nobody's there. But it's almost throughout the entire nighttime. So if it happens for seasons and years at an end, you might get things like mold growth and all sorts of other problems. So this actually was kind of useful for us to see that this additional complexity that you have to deal with in designing this controllers that also not only optimizes our temperature but also humidity is actually worthwhile in the long run. So that's the summary. So the goal is autonomy. So we want to make sure that the models we use can be learned online, and they are designed in a way that they make your optimization problem nicer in a way, right? So we make sure that we use linear time varying models. So optimization is always convex. There's a feasibility part which I did not touch upon, but we can guarantee that as well to some extent. But because they are linear, so the optimization problem becomes convex, and the method we use to identify the models, that method is completely automated. There's no human intervention needed at all. It's guaranteed to always give you a solution and a unique minimum solution. So you can put that as a software module that goes into your overall controller, and you never have to worry about it. You never have to say, oh, the controller said you cannot identify a model for next week. Some expert needs to go in and change some parameters. You'll never have to do that. So that's the kind of basis for autonomy. Now we're not completely there because some of the equipment models we are still not able to get linear models that give us the performance that we need. So we are struggling with that. And the MPC controller with humidity, again, given that we are in a dry climate, this may not be a super important comment here, but in Florida, this is really important that once you have to have humidity in your problem formulation, although it makes the problem more complicated, but you actually, if you don't do that, then you'll seriously screw up. So future work, modeling of chillers and cooling towers, because that's the part we have completely ignored so far because of the building that we are trying to do experiments. We are not done yet. We're building up towards the experiments. That building kind of allows us to separate the cooling towers because we get chilled water from a district cooling and heating, a district cooling plant. So there's a chiller plant that supplies chilled water, so we don't have to worry about that so far. So that was, and there are some references here if you're interested. That's all I want to talk about for this talk, but I know that my good friend Dusgun Agdas was here for some time, and he probably mentioned some of this work that I'm working with him on. So this is another project that's going on, but not optimization for energy, but for occupant comfort. So one of the things that I realized after working on this for some time, I was trying to pitch it to industry, or maybe even talk to startups or talk to people who are interested in creating startups. And I realized that there is not a whole lot of market for energy efficiency. Although people say, yeah, energy is important, we want to reduce bills. Nobody really cares about energy because energy bill is actually a small fraction of the overall cost of managing a facility. The biggest driver is occupant comfort. So if you can, because that ties to productivity. Productivity has a huge impact on your total, your bottom line than energy. So one of the things we're trying to do is do personalized comfort in these shared spaces. That's an interesting kind of control problem. The biggest problem that we were facing in the beginning was, well, how do you measure comfort? There is no sensor you can buy from Home Depot to measure comfort. So we created this sensor, which is this device. It got a whole bunch of sensors in the back that you don't see, but there's a touch screen. So the user can kind of, using the touch screen, provide feedback. I'm hot, I'm cold, I'm extremely hot, extremely cold, or I'm comfortable. The idea is that once we get enough data, and that's a big if we get enough data from occupants, then by using the other environmental variables that are also measuring, we can come up with a model for each person, right? So under what environmental conditions is this particular person most comfortable? Once we have that model, then we can design a controller to kind of keep each station in that envelope. So that's another one that's going on. So yeah, finally, thank you for your attention. That's my website, contact information. I also have other personal website, and this is the logo for my lab. All right, I'll try to remember. Yes, I'll try to remember that.
I'll start.
I was going to ask, are you controlling only the conditioned air temperature, the supply air temperature of the room? Those two variables that you're actually controlling?
Controlling 4 variables. So at the, oh yeah, the question is, am I only controlling the conditioned air temperature and the supply air temperature? So after the cooling column, after the reheat, reheat coil. Those are not the only ones. There are other two things, because we're talking about the air handling unit. So we are also controlling two other variables. One is the total airflow rate, and the other is the return air ratio, because together they determine the ventilation. So there are 4 variables that we're controlling. Yes.
When you say convexity of the problem, are you referring to the parameter space that you're allowed to choose from, or something about the cost function?
So it's both. So when I say convex problem, optimization problem is minimize some cost subject to some constraint, right? So for that problem to qualify as convex, both the cost function has to be a convex function, but also the constraint set, the region in the space where you're allowed to search from the constraint set also has to be a convex set.
All right, so what is a convex function?
So convex function is, if you, I mean, say y equal to x squared is a convex function. All right, so there's a technical definition that if I had a board, I could, the technical definition is that if you go from any average point has to lie above the value of the function. So best way to think about convex function, think about a well that looks like this. A function that looks like this is a convex function. So yeah, if a concave function, flip it, it becomes a convex function. Yeah, concave is fine too, but then if you concave, then you have to solve a maximization problem, because convex function looks like this, right? Oh, I forgot to repeat the question. The question is, what is a convex function, right?
The important thing is that all local minimums are global.
Right.
Well, if it's convex, when you only have one minimum.
So it's strictly convex, only one minimum, precisely one. But the technical definition, convexity allows you to have many local minimum as well, but all of those local minimums are also global minimum. So like a linear function is technically also a convex, but not strictly convex.
So you have multiple minimums,
but they all have the same cost. So if you are in that situation, there are multiple minimum, you can pick any minimum and you would be equally good. Right? Of course, that's not, yeah, you don't want that situation so much. What you want is a strict convexity, so there's a unique minimum. All right. Yes?
My question is, so related to your question, I understand the importance of convexity. You're prioritizing speed, since one of your objectives moving into this research was near real-time solutions that are fully autonomous.
Right, right.
Can you speak to the role of cloud computing today and as you see it in the next 10 years?
Cloud computing, yes. The question is, can I speak to the role of cloud computing today and next 10 years? I mean, cloud computing is, yeah, so there are pluses and minuses, right? So I would say there are pluses and minuses. So I didn't report any experimental evidence today, but I have done some previous work where we actually did model predictive control to this building that we did, this Pew Hall test bed that I was showing you. So we, of course, you know, of course, the control computations were done in the cloud, quote unquote. I mean, the cloud in that case was a computer in my lab, and the commands are being sent over the campus network to the floor level network controllers in the building, and we are overwriting the backnet commands from the BAS using higher priority. So if you are going to, especially for this level of complex control systems, you are probably better off using cloud computing, because then you can offload the job to some other computation platform, and you're not limited to what's in the building. Also because these need, so the building automation system have their own compute platforms, but they are not designed for general purpose computing. You cannot have linear algebra packages there, right? So if you want to do this sort of optimization, you have two options. Either you have to augment that system with an extra processor that can do general purpose computing, or you offload everything to the cloud, right? So I would say pluses and minuses. The plus of cloud computing is that all you need is internet connection, right? And because we are doing planning for the next 24 hours, we are kind of robust to communication failures for a few hours. So if you lose communication for a few hours, no big deal. It already has a plan for the next 24 hours. It'll just go on implementing that until it gets the next one. So it'll be suboptimal for those few hours, but not a big deal, right? But I think the bigger problem that the building operators are concerned about when I talk to them is things like cybersecurity, right? So it took me, before this pew hall, like I call it living laboratory. It took me years worth of meetings, going from all the way from VP of facilities to down to the person who fixes the light bulbs, to make sure that everybody is on board. And the biggest pushback I got was from the campus IT people, right? So because and it's a serious concern, nothing to be laughed at. How do you make sure that nobody hacks my system through your this port that you're opening up? So they are kind enough at the end to open up a port to their VLAN, because the building automation packets go through their own VLAN. So if cybersecurity becomes a serious concern, maybe you're better off, especially if these things are picked up by industry, of adding an extra processor on the building automation system, because if you've done it large scale, it's not that expensive. So then you just send a few things over the internet, maybe one way, but not bidirectional communication, which is when things get more complicated, right? Yes.
Along the lines of cloud computing, as we start running all of these optimization problems for the purpose of energy efficiency, of course, there's going to be sort of an energy penalty to calculating this, especially in the cloud, all the networking, running all that. Do you happen to know like order of magnitude efficiency penalty we're talking about for adding all the calculation, computing energy?
So the question is, if we start doing more complicated calculations, will there be an energy penalty because of the calculations, and how much is that compared to the energy we are saving? My guess is that's minuscule. I mean, that's like one computer. At the worst case, you'll have one computer running full time, your algorithm. That's one computer in a building. So, right, we already have hundreds of computers in a building. That plug loads are like what? A small fraction of the total energy use. So, yeah, I would not worry about that so much. Yes.
Have you thought about using some sort of predictor of the occupant disturbance? Like, I mean, some ideas that I could think of would be like some information on your electric load, or plug loads, or lighting, or something.
Right.
Or wireless.
Class schedule. Right.
Wireless connectivity.
Wi-Fi.
Wireless network.
Yeah, so that's an excellent question. The question is, I guess, I'm going to rephrase your question. You tell me if I'm rephrasing it correctly. Is that what other information can I use to come up with better occupancy prediction, which will help me with all these other disturbance predictions? Is that correct? Yeah. Okay. So yes, there are a whole bunch of things. I mean, there are already, I think, commercial solutions. You can use Wi-Fi packet sniffing to tell you how many additional devices are there, which may tell you something about people. You may look at even demand patterns, plug loads, and I mean, there's no limit. You can use even actual occupancy sensors, thermal cameras. It's a little bit expensive, but the technology is being developed. So yes, I definitely want to use all of them. I have not really done that yet, because the problem is you immediately have to add extra sensors. That adds not just cost, but complexity in integration. So I'm trying to do everything I can do with just existing infrastructure without asking for extra. That causes trouble in terms of like implementation or integration. So if a building has that information, great. I can definitely use that immediately and augment my algorithm to come up with better prediction.
How big a disturbance do you see in your control from maybe errors in when that occupancy pattern changes, when it's not?
How big it? Oh yeah, how big a disturbance?
When you have the big offsets, one direction or another.
Are you asking about the heat load caused by the occupants?
So then it should predict something, and then maybe your outputs on your internal temperatures are outside the balancing effect. You ever see that? Say a bunch of people come into a room.
Okay.
You're making a prediction that there's not many people.
Right. Okay. So the question is, I guess, sensitivity to these occupancy type predictions. Yeah. So we have not seen that because we haven't run those simulations yet. I'm sure there you will see those spikes. So I mean, you're talking about predicting, overall heat load, heat gains from occupants, and there is you cannot get that too accurate. There's just no way, right? So there will be times when there's a large disturbance because of occupants that your model did not predict. So yeah, that will lead to a spike. But although we are optimizing over this, using these predictions, remember the big thing about MPC, why it is better than just open loop optimization, is that you optimize and 5 minutes later you re-optimize. And so when a big spike like that comes in, it'll get reflected in the measurements of temperature and things like that. So the MPC will pick that up and it'll correct it to some extent. So at least it may not be that, it may not save that much energy, but it'll make sure that the spikes in temperature will get rejected pretty soon. Yes. Yeah, no, so the chillers and all the cooling towers, that part is not taken care of right now. Yes, that's something we need to do.
So, I mean, I've read some of these papers, and I recognize them in terms of management as well. A lot of these MPCs seem to get a big efficiency gain by hugging one side of the dead
Yes.
temperature.
By hugging one side of the dead. Okay, all right.
In cooling, it's normally like the hottest temperature can be, in cooling or in heating, it's normally the coldest temperature. How do you haven't thought of it in terms of what equipment efficiency might change that response, since you're not necessarily going to want to, you may want to use more of that deadband instead of just sticking to one side of it?
So the question is, a lot of these MPC algorithms tend to get the efficiency gain by sticking to one side of the deadband. So if it allows you to be, because there's always a non-zero deadband, it allows you to be at any location within that. And if the outside is hot, then it helps energy efficiency by staying on the hotter side, right? So I don't know how that relates to the equipment efficiency. Now, if you're concerned about, well, if you're always sticking to one side of the deadband, and that's bad, then I would say you should reduce the deadband. So that kind of goes back to the question of, what are the right environmental conditions for people, right?
Sure. I mean, it's more of like, as it gets hotter throughout the day, your cooling equipment's going to operate less efficient, so your cost function is going to change.
Right. Well, if that's the case,
The prediction might be 5 minutes, which is kind of whether it's set up in a way that you can take that opportunity to leave one side of the deadband to potentially save more energy.
I see. Right. Yeah, that's a. I don't have anything useful to say to that. You might be right. Maybe if you include the equipment efficiency curves and all their operational constraints, it may so happen that it's not always efficient to hug the one boundary, right?